Here's an audio-friendly summary of the Chinchilla paper. For years, the recipe for building better language models seemed straightforward. Make them bigger. GPT-3 had 175 billion parameters. Gopher pushed that to 280 billion, and Megatron-Turing reached 530 billion. But here's a curious pattern hiding in plain sight. Almost all of these models, despite their wildly different sizes, were trained on roughly the same amount of text, about 300 billion tokens. This paper from DeepMind asks a deceptively simple question. When you have a fixed compute budget, how should you split it between making the model bigger and feeding it more data? The answer turns out to overturn the conventional wisdom and produces a model called Chinchilla that, at 1/4 the size of Gopher, beats it on essentially every benchmark. To set the stage, training a large language model has a kind of inescapable arithmetic. The total compute you spend is roughly proportional to the number of parameters times the number of training tokens. So if you double your compute budget, you have to decide, do you grow the model, train on more data, or both? Back in 2020, Kaplan and colleagues published an influential study suggesting that when compute grows by 10 times, you should grow the model by about 5.5 times, but only grow the data by less than 2 times. This recommendation essentially licensed the race toward ever larger models. Think of it like a chef given a bigger kitchen budget and being told to mostly buy a fancier oven rather than better ingredients. The whole field followed this advice. The DeepMind authors revisit this question with a much more thorough experimental setup. They train over 400 models ranging from 70 million to 16 billion parameters on datasets from 5 billion to 500 billion tokens, and use 3 independent methods to figure out the optimal trade-off. The first approach fixes a set of model sizes and varies how long each is trained. Then for every possible compute budget, asks which model size achieved the lowest loss. The second approach, called iso-flop profiles, fixes the compute budget and sweeps model size, looking for the bottom of the U-shaped curve where loss is minimized. The third approach fits a parametric formula to all the training results, modeling the final loss as the sum of 3 terms. An irreducible entropy flaw, representing the inherent unpredictability of natural language. A term that shrinks as the model gets bigger, and a term that shrinks as you train on more data. By fitting this formula and then minimizing it subject to the compute constraint, they derive closed-form predictions for the optimal model size and dataset size. Here's the key insight that distinguishes this work. The earlier Kaplan study used a fixed learning rate schedule for all their runs, regardless of how long each model was actually trained. The DeepMind team discovered that this is a subtle but consequential mistake. The cosine learning rate schedule, which gradually decays the learning rate over training, needs to be tuned to the actual training length. If you set the schedule to decay over 130 billion tokens, but stop training after only 30 billion, your intermediate losses look artificially bad, which makes shorter training runs look worse than they actually are. Imagine judging a marathon runner's pace by checking on them at mile 5 when they've planned their energy distribution for the full 26 miles. Once you correct for this and let each run use its own properly matched schedule, the picture changes dramatically. All 3 methods converge on the same striking conclusion. For compute-optimal training, model size and training tokens should scale in roughly equal proportions. If you double your compute, double both the parameters and the data. This is profoundly different from the earlier recommendation that emphasized scaling parameters far faster than data. Their estimates put the exponent on parameters at around 0.46 to 0.5 U and on tokens at around 0.50 to 0.54, compared to Kaplan's 0.73 and 0.27. The practical implication is jarring. Their analysis suggests that GPT-3 at 175 billion parameters should have been trained on around 4 trillion tokens instead of 300 billion. Gopher should have been a 70 billion parameter model trained on 1.5 trillion tokens. The largest models of the era were essentially starving for data. To prove this isn't just curve fitting, the authors put their money where their math is. They take the exact compute budget used to train Gopher and instead build a 70 billion parameter model trained on 1.4 trillion tokens. They call it Chinchilla. The architecture is essentially identical to Gopher with a few minor tweaks, switching from atom to atom W for the optimizer, a slightly modified tokenizer that better handles math and chemistry, and a higher learning rate suited to the smaller model. The results are remarkable. On the MMLU benchmark, which tests knowledge across 57 academic subjects, Chinchilla hits 67.6% average accuracy compared to Gopher's 60%. That's a 7.6 point improvement, and it actually exceeds the forecast that expert human forecasters had made for what state-of-the-art models would achieve by June 2023. Chinchilla wins on reading comprehension benchmarks by margins exceeding 10 points, sets new state-of-the-art on closed-book question answering, and beats Gopher on 57 of 62 big bench tasks. And because it's 4 times smaller, inference and fine-tuning cost dramatically less. Now for the limitations the authors acknowledge or that lurk just beneath the surface. They only have 2 large-scale runs to validate their predictions, Chinchilla and Gopher. There's no intermediate scale verification. They assume a clean power law relationship, but they actually observe some curvature at the larger scales, suggesting that truly enormous models might benefit from an even more data-heavy mix than their power law predicts. They train on less than 1 epoch of data, so the multi-epoch regime where you might revisit tokens remains unexplored. Perhaps most importantly, their conclusion implicitly assumes that high-quality data is available in arbitrary quantities, which becomes increasingly questionable as we push toward trillions of tokens. Web-scraped data at that scale brings serious problems around toxicity, bias, privacy, and the simple question of whether enough quality text exists at all. The forward-looking implications are substantial. The entire field's emphasis on parameter count as the headline metric of progress turns out to be misguided. A smaller, well-trained model is both better and cheaper to deploy, which matters enormously when inference costs dominate over the long lifetime of a deployed model. The bottleneck for further progress shifts from raw engineering capability to dataset curation, and that change in emphasis has rippled through everything that came after this paper. Now let's walk through some questions you might have after hearing all of this. First, why did the earlier Kaplan study reach such a different conclusion if they were studying the same phenomenon? The core issue was the learning rate schedule. Kaplan used a single fixed schedule across all training run lengths, so when they looked at the loss partway through a long planned run, that loss didn't represent what a model would actually achieve if it were properly trained for that shorter duration. This systematically made shorter training runs look worse, which biased the analysis toward recommending bigger models with shorter training. The DeepMind team also used a much wider range of model sizes, including more large models, whereas Kaplan's analysis was dominated by smaller runs. Second, if scaling data and parameters equally is optimal, why doesn't this also mean we should just keep growing both forever? In principle, you can, but you hit 2 practical walls. The first is that high-quality text data is finite. Estimates suggest the entire usable web is in the low tens of trillions of tokens, and quality drops sharply as you scrape more aggressively. The second is the curvature in the relationship that the authors observed at large scales, hinting that the clean power law may bend. So the recipe works wonderfully in the regime they tested, but extrapolating it to models with trillions of parameters likely requires either much more data than exists or new techniques like retrieval, synthetic data, or training for multiple epochs. Third, why does a smaller, longer trained model end up so much better, rather than just equivalent at the same compute. The intuition is that a giant undertrained model has tons of capacity, but hasn't actually used it effectively. Most of its parameters haven't been refined enough to encode useful patterns. A smaller model that sees 4 times more data has fully exercised its weights and pushed deeper into the patterns of language. There's also a quiet bonus. The smaller model is dramatically cheaper to run after training, which compounds over millions of inference calls in deployment. So you're not just getting equal quality at lower training cost, you're getting better quality and dramatically lower serving cost. For large-scale recommendation systems, the lessons from Chinchilla translate directly even though the domain looks different. Industrial recommendation models, especially the transformer-based sequence models used for user behavior modeling, have been scaling up rapidly in parameter count, often without a corresponding rigorous look at how much interaction data each parameter is actually getting. The Chinchilla framing suggests teams should treat the trade-off between model size and the volume of user interaction sequences as a first-class optimization, fitting their own scaling laws on smaller pilot runs before committing to expensive large training jobs. This is particularly relevant for two-tower retrieval models and for ranking models where serving latency caps how big the model can be. A compute-optimal recommendation model might be smaller than current trends suggest, trained on far more interaction history per parameter, which yields both better offline metrics and crucially lower serving costs. The other practical insight is around data quality and freshness. Recommendation data is generated continuously and at enormous scale, so unlike text, where you eventually exhaust the web, recommendation systems have a near infinite stream. This actually makes them an ideal setting for data-heavy compute-optimal training. The challenge becomes filtering and weighting interactions, deduplicating near-identical sessions, and being thoughtful about temporal distribution shift. The same care the Chinchilla authors call for in text data curation, but applied to behavioral logs.